Hey there, awesome physics students. Let's talk about what controls the frequency of oscillations. Before we get into the details, let's talk about frequency for just a second. Frequency, we use the letter F for that, and it's measured in cycles per second. But unfortunately, nature does not like cycles per second. It wants a different unit. So let's think about oscillations, or going around a circle one time. That's equal to one cycle. Which is also going around in a circle once, is 360 degrees. Nature doesn't like either of these units. Nature likes radians, and so if you remember, going around a circle once is 2 pi radians. So we need to convert this from cycles per second to radians per second. So if we have frequency in cycles per second, I want to get rid of the cycles, so I want to divide by one cycle. But one cycle is equal to 2 pi radians, so we put that up top because I want that to be in the numerator. And if I multiply this out, this gives me angular frequency. We use the Greek letter omega for that. It looks like a W. You can call it a W, but just know that you're wrong. It's a Greek letter omega. And this is called angular frequency. It's just 2 pi times the regular frequency. Now, know that these measure the same thing. They represent the same thing. They just have different units. Okay, so with that in mind, let's talk about the main idea here, what controls frequency of oscillations. In all oscillating systems, what controls the frequency is some measure of the restoring force to some measure of inertia. Okay? And we have this square root in there too. So generally, if we increase the restoring force in a system, that's going to produce a higher acceleration, which is going to allow it to oscillate around its equilibrium position more frequently. And so increasing the restoring force is going to increase the frequency. Likewise, if we increase the inertia is its resistance to change in motion. If we increase that, it's going to become more sluggish, or it's going to reduce the acceleration, which means it's going to oscillate less frequently. Okay, so let's think about this for some common systems. One system that we are going to talk about over and over again is a mass on a spring. So if you have a spring constant K and a mass M, how would we find the frequency for this system? Well, K represents the strength of the restoring force in this case. And m, the mass, represents the measure of inertia. And so for this system, the frequency is just the square root of k over m. And if you do the math on that, the units actually work out exactly like you want radians per second. Now what happens if we increase the restoring force on this? How would we do that? Well, one way to do that is to just put another spring on there. And so we effectively double the spring constant, or put another double the restoring force. So if the spring constant doubles, what effect does that have on the frequency? Well, the doubling, you'll notice, occurs underneath the square root. And so this actually doesn't double the frequency, but it increases the frequency by a factor of square root 2. So it's not exactly what we want. If we wanted to double the frequency, I would need to quadruple the restoring force. I would need to have 4 times as much restoring force, or 4 times the restoring force, and then the frequency would go up by a factor of square root of 4, which is 2 times bigger than what it was before. Okay, so what happens if we take this simple toy system and take the mass, increase the mass? So if we take the mass and double it, what happens in that case? Well, again, looking here, the doubling is going to occur in the denominator, but still underneath the square root. And so the frequency is going to go to 1 over square root 2 times the frequency. If we want to if we want to have the frequency of this system, I would need to add 4 times as much mass. Okay, let's think about some real systems that are physically relevant. Let's think about a guitar string, for example. If you want to lower the frequency in a guitar string, one way to do that is to take the guitar string and increase the inertia by just wrapping steel wire around the guitar string. And the effect that has is the mass of this guitar string will go up, which will make the inertia go up, and the the frequency will then decrease. So this will be a very low frequency instrument, and this is what you see on bass guitars. They have very, very thick strings because they need to have a very low frequency. Another way to change the frequency of a guitar string, if you think about what causes it to oscillate back and forth around its equilibrium position, that's the tension in the string. And so if I increase the tension in the string by just making the string tighter, then the effect that's going to have is increase the restoring force. If I increase the restoring force, that's going to increase the frequency. And actually, this is what you do when you tune a guitar, is you just tighten or loosen the string. That changes the tension, which changes the frequency until it's in tune. Lastly, let's think about what happens in our vocal cords. I can't change the inertia of my vocal cords because that would be the mass of my vocal cords. How do I change the frequency? Well, I just have to change the restoring force, and that's the tension inside my vocal cords. So if I want to increase my frequency, I just tighten those vocal cords. And if I want to sing really low, then I just loosen those vocal cords, and the frequency will go down. Okay? So the overall idea here is for all oscillating systems, the frequency is controlled by some measure of the restoring force to some measure of the inertia, and I have the square root in there as well. All right?